I'm Bonari. Actually, I'm currently a postdoctoral researcher in Marco's research unit. I'm going to present a work related to the development of a simplified approach for the solution of contact problems involving rough surfaces. The motivation behind this study is that most of natural and artificial surfaces are characterized by fractal properties that go down to the microscale of the surfaces themselves. Fractality is a feature common for many natural surfaces, and its study is important because, in spite the geometrical characteristics are only appreciable at the microscale of the surfaces, their importance scales up in such a way that it affects the contact behavior of the two bodies also at larger scale. For example, it affects the adhesiveness of the spatula of the Jacofit. It has consequences for electrical and thermal exchanges in silicon. For example, it plays an important role in the super hydrophobicity of certain leaves, and also in creation of fracture in solids, and also defines the shape of other artificial materials, for example, asphalt. For this reason, it's very important to take into account the exact geometry of two bodies when we have to analyze their contact interactions. Currently, there are two main numerical approaches for the study of contact problems involving rough surfaces. The first is the boundary element method, which is based on the convolution of the forces exerted by a rough surface on an elastic continuum. It has some good features. For example, it doesn't need any assumption on the asperities shape, so that we can choose in total freedom the geometrical features of the body. It's rather fast since it only deals with the surface, so we don't have to take into account the bulk, what lies between. The elastic interactions between two different asperities can be taken freely into account, but it has the severe drawback that is mostly restricted to linear materials and very simple geometries. On the other hand, we have the other very common method for the solution of this, for the analysis of this class of problems, which is the finite element method. It is characterized as the boundary element method by the no need for any a priori assumption on the geometry of the body. It can be successfully applied to any constitutive model and any complex geometry. And because of this feature, is much more versatile, let's say, than the boundary element method. And it's, on the top of that, it's also easily extensible. It's easily extendable for taking into account also multi-domain and multi-physics phenomena. Of course, this comes with a cost, and the cost is that it's a bit more cumbersome to be employed than the boundary element method, because if we have to take into account very fine geometrical features, the complexity of our model is affected in such a way that if we want a very geometrically accurate model, the computational costs become very very, very high. For these reasons, we decided to define a simplified method, which is based on the finite element method, which allows us to cut a complexity, which is having to exactly define the complex geometrical features of our rough surfaces. We can do so by applying an a priori hypothesis, which is that one of the two contacting bodies, in this case B2, is rigid and characterized by a rough profile. While on the other hand, we can consider the other body in contact B1 to be characterized by some degree of smoothness. In such a way, we can define a function z of x, which maps the original exact height profile of the rough surfaces, of the rough surface, and stores it into an appropriate variable. By doing so, we are allowed to totally reshape the original geometry of the model by considering an equivalent model which is much simplified. And at this point, we are dealing with a different problem, of course, because we are getting rid of all the complexities related to the original rough geometry, but since we have stored the original height in the variable z, we are actually able to recover the original condition of the problem by suitably defining a modified quantity, which is the normal gap, which maps the contact zone of our problem and restores the original contact conditions of the complex problem. So basically we have this quantity here, which is related to the normal gap between these 2 points in the, let's say, simplified configuration, which is then corrected to restore the original height field. We are then able to plug our configuration, our formulation inside the framework proper of the finite element method, which foresees the discretization of the whole of the two bodies, as we have seen in the beginning. And this could be done by the definition of a suitable interface finite element, which connects the two bodies in contact. We might have a 4-node quadrilateral elements for two-dimensional problem, which come into contact over a profile, or we can also have an hexahedral interface finite element if, of course, we are analyzing a 3-dimensional problem. Once we have defined the kinematics of our interface finite element, we are also able to solve this problem in a rather, let's say, standard way by invoking the principle of virtual work and defining the first variation of the energetic contribution of the contact interface, which directly depends on the quantity that we have defined before, so the corrected normal gap, and the contact traction, which is a vector that stores the forces which are exchanged in correspondence of the contact points of our two bodies. So once we know both this quantity and the forces at the interface, we have all the ingredients that are necessary for the solution of our problem. As we can see here, there is a relation between the displacements, which are the unknowns of our problem, and the forces that are exchanged at the interface. And we might define a direct relation between the displacements expressed in terms of normal gap Gn and the forces in both the normal direction and horizontal direction by defining a regularized contact law. For example, for the normal direction, we can invoke a regularized penalty approach, and the same can be done also for the tangential direction, defining a regularized version of the classic Coulomb friction law. Once we have defined a constitutive relation for the interface in terms of normal and tangential reactions, which means once we have defined a direct link between the forces and displacements, we have all the ingredients for the solution of our problem. So we have here, we have a little, say, toy example. As we have seen before, here we have the standard normal gap, and this would be valid exactly for the solution of a contact problem characterized by two flat interfaces. If we want to solve a contact problem like this, in which a rigid sphere is indenting an elastic body, we are able to recover these modified contact conditions very simply by perturbing the normal gap by a quantity which approximates the shape of our sphere. And the results in, let's say, physical terms is this. Here we have our elastic bulk, which is part of the problem. And then we have our rigid surface, which doesn't appear directly in the problem, since it's only defined by this, since it's only defined in mathematical terms, and it's only been added to the sketch for the sake of representativeness. And this is a very simple example, but we can also do something more. So we tested the same implementation against a more complex surface. For example, here we have a wavy surface characterized by the superposition of a sine wave in two directions. The same problem, so we have this rigid wavy surface indenting a half space. The same problem has been solved using our modified finite element implementation, and the results have been compared to a reference solution obtained with a different numerical models. And as you can see from both this plot and this surface plot, the agreement between the two solutions is very good. Here on the right, here this figure represents a plane view of the traction of the normal tractions field over the interface. On the right side, on the left side, you can see our solution, and on the right side, we can see the reference solution, and we can notice that there is perfect agreement between them. So far we have only plugged into the model very simple shapes, which could be defined using analytical function, but this is not our scope. because we want to analyze rough surfaces, which cannot be defined in a simple way. So the next step is to using our implementation for the solution of totally rough contact problem. For doing so, we need, first of all, a rough surface. Rough surfaces could be either synthetically generated or sampled from experiment. For what concerns synthetic rough surfaces, we have mainly three methods which are employed for their generation. The first one is called the spectral synthesis method, which exploits a property of fractal surfaces, which is that their spectral density function is logarithmic linear, so that we can define a priori the power spectral density and then map back the original 8phi by an inverse Fourier transform operation. The second possibility is to use a random midpoint displacement algorithm, which is a recursive algorithm that generates a rough fractal surface characterized by a specific desired characteristics. And this is very interesting because, as a side note, it's the same algorithm that is employed in computer graphics for generating landscapes or hill shades or terrain and so on. And finally, there is a third method, which is the so-called Weierstrass-Mandelbrot function, which is a very simple way for generating fractal surfaces because it's an analytical definition of a fractal surface, so ready to be used. In the following example, we have used the spectral synthesis method for generating a rough surface, which is characterized by its power spectral density. On the red line, it's the original power spectral density imposed for the generation of the surface with specified characteristics, and the dots are the dots represent the power spectral density of the synthetic generated surface. It has similar properties to an asphalt sample, which could be used, for example, in a contact context for the analysis of friction coefficient between tire and asphalt. We have defined our bulk, which is characterized by a very fine interface for capturing all the relevant geometrical features of our problem. And in the animation, we can see the normal traction field, which generates from the contact. You can see that by applying pressure on the surface, there is contact, which is spreading, of course, starting from the bottom points of the surface and then propagates all across the surface. And this is rather satisfying results because so far this problem solved using the finite element methods would be very difficult to be addressed using let's say standard implementation. But of course we want to go on. We want to go further. So we would like to use our method to address the so-called contact mechanics challenge, which is a challenge set up by two two researchers 5 years ago, which wanted to define the state of the art of contact models employed for the solution of a rough problem. And so far, no solution has been attempted using the finite element method, and this is our goal. And of course, to conclude, I would like to sum up the key features of our model, which is the direct integration of analytical functions or fields, which could come directly from experimental, for example, from both the atomic force microscope or the profilometer, which is present in our lab here in Lucca. We have a full bypass of the most common problems which characterize the solution of these kind of problems using the finite element method. And finally, it fosters a directly data-driven simulation for this kind of problem. You have actually an ongoing collaboration with NEST for the application of surfaces acquired using atomic force microscope to our scope. And this concludes the presentation. I would like to leave you with some references if you are interested in delving to the topic. I would like to thank you for your attention, and that was it from my side. Thanks again.